everybody for this special IISc and Academy public lecture. Thanks Academy for hosting this. It's a pleasure to have Bill Goddard for the session today. Many of you might be knowing him, but nevertheless I'll just introduce him. So Goddard has been a pioneer in developing methods for quantum mechanics, force fields, reactive dynamics, molecular dynamics, complete sampling predictions. In fact, any areas of computational chemistry, computational physics, he has some contribution. So his education is, he did his PhD from engineering science, minor in physics from Caltech in 1965. And after that, he joined as a faculty in Caltech in chemistry, and he is there ever since last 60 years.
So I actually joined November 64.
Oh, November 64, okay. Okay. So he is the director of what is called the Materials Process and Simulation Center, where I spent some time several years back. It is a large, big group. So he is very prolific. He has written almost 1,600 papers by now. Even now also he writes 20-30 papers a year. And he is highly cited. He is one of the highly cited researchers in last several years by ISI. In fact, in a recent indexing, he has been ranked as number 12 scientist in USA and number 17 scientist in the whole world, based on some D index. He has been elected to the National Academy, US National Academy of Science in 1984, and he has been awarded several other honorary degrees from all over the world. And his main focus is to, as it is written in the abstract, that to optimize performance computationally for many systems and materials, so the experimental valuation can be restricted to the predicted set of things. And he has been a great mentor. He has mentored almost hundreds of students, or more than hundreds.
Yeah, about 180.
180 students and postdocs who are all over USA, all over world, and it's great to have you, Bill.
Okay, well, it's good to be back.
Thanks for forward to hearing from you. So, Bill, over to you.
All right. So, I'm planning to talk today about some work we're doing on lithium metal batteries. We're very excited about getting electrolytes that are stable with lithium metal, so we can get 4 to 10 times more power. And I'll talk about the SEI formation, reactions with electrolytes, some of the conductivity. And then I'll talk about the new methods we developed for looking at electrocatalysis we call grand canonical methods. So these are constant potential within constant electron. And I'll talk about 3 examples we've applied this to. And then I'll talk about a brand new paper. It just came out. Looking at the pK of metals, of water near metal surfaces. So there are a lot of efforts right now going on to try to measure the pK, but most experiments don't get closer than about 1 micron. And so, and then I'll talk about, to compare with experiment, we need to do the vibrational spectrum at the same temperature as the experiment. So we call that operando. And then I'll talk about some of the react force field things we've used for different reactions, oxygen reduction, and maybe some CO2 reduction at the end. So, so these days in my group, we sort of focus on the problems we want to solve. And so we really want to look at water splitting, hopefully driven by photons, CO2 reduction to useful things like ethanol, fuel cell catalysts that are many times faster than the current oxygen reaction, batteries, looking at electrolytes that are stable with lithium electrodes. So we want to design new solutions from first principles and do the in silico part across the board with the theory, and try to end up with the very best cases to do experiments on. And so we develop new methods. Usually, if the methods already exist, probably someone's already using them to look at the problems. We tend to focus on the cases where the methods don't yet exist. And so I'll talk a little bit about the grand canonical method, maybe some metadynamics, and these react force fields. And so what I consider a couple of recent breakthroughs is this grand canonical reaction kinetics. which I'll talk about. And I'll give the examples: the water splitting, hydrogen evolution, oxygen evolution, CO2 reduction. Also, the Reax force field, which we developed 30 years ago, it's really coming into the fore now because quantum mechanics is good to up maybe to 300 atoms and maybe 20 or 40 picoseconds. We really need to do systems that are 10 nanometers, that's 100,000 atoms, 30 nanometers, that's 1,000,000 atoms, and we want to do reactions. And so, this works pretty well. So the issue with lithium is the current generation is lithium ion. That means you put the lithium ions into graphite, that's charging it, and then it goes off to discharge it. But what you really want is lithium metal. And so the problem with lithium metal is it's very reactive, reacts with the electrolyte. So we want to understand that. And we're also, in terms of the electrolytes, we want to look at sulfur-based systems. So not S8-based, but PS4-based systems. They have a lot of advantages. And for both the electrolyte and for the cathode. So, yeah. So this is a schematic representation of system we studied. So we had funding from LG Chem to look at ionic liquids next to lithium electrodes to understand what the issues are. And so we focused on the ionic liquid interface with lithium metal, that interface. And we had no idea what was going on because experiments just basically give you no information about interfaces. That's the real role for theory, is figure out what's going on at the interfaces. And so we want to look at this interface that forms in between the ionic liquid and the lithium metal. And so, so this is a schematic representation. We have an ionic liquid. The one we're doing is a TFSI. This is the anion. And then there's an organic quaternary nitrogen, and then a dope with lithium for the transport. And that's next to the lithium metal. So we want to see what kind of SEI forms between them. So there's ionic liquid, there's SEI, really this is one system, and the lithium metal. And so what we did,
Questions?
yes?
Sorry, what's an SEI?
Oh, solid electrolyte interface. So generally, there may be a reaction between the electrolyte and the lithium anode, and then you get an in between them. You could call it the electrode-electrolyte interface, EEI, or solid electrolyte interface, but it's the interface between the electrolyte, in this case ionic liquid, and lithium metal. It's reactions that go on, and we don't want a very big SEI, and we want to have good connectivity.
So is this something that is by design, or does that...
But it happens automatically. But it's been hard to study experimentally because it's right at the interface. It's only, nanometers wide. And so people have speculated on it, but there's almost no characterization experimentally of what it actually looks like. And so very important, we think, to look at the theory. And so what we did is we looked at this interface with full quantum mechanics. Now, the problem with quantum mechanics is it's hard to do more than 200 atoms, maybe 300 atoms, and it's hard to do more than 40 or 50 picoseconds. We actually did 150 picoseconds of dynamics to see what happens when this anion is next to lithium metal. And what we found is that at the end of the day, that all of the organic had broken bonds. The TFSI, we broke the CF bonds, the S bonds, the SO bonds, the S nitrogen bonds, everything got broken, and all these parts of the anion were only bonded to lithium. So no one really knew for sure. That came out of the quantum mechanics. But the problem with the quantum mechanics is it's only 200 or 300 atoms. It's only 2 or 3 nanometers. So it's not really enough to get a full representation of the system. So what we did so we used the quantum mechanics to get that the SEI, the interface, and what we found was the cation is pretty stable, a very, very little reaction with that, and that the molecules completely broke apart. And so, and this is just more on that, looking at the different levels, different temperatures. But the point is, all the systems we did, they completely break apart into atoms. And so this shows the distribution. Actually, the density of lithium in the electrode and the density of lithium in the SEI is about the same. So you have concentrations. You have carbon and fluorine near the lithium electrode. You tend to have nitrogen, oxygen, sulfur near the electrolyte. That all came out of the quantum mechanics. So we learned a lot, but it's not useful to characterize a real system. We need a system that's maybe 50, 100 nanometers long. We need to have plenty of room. There's ionic liquid and there's metal. We need somewhere between 50,000 and 100,000 atoms. But quantum mechanics, basically going a bunch above 300 atoms is way too slow, a bunch above 2 nanometers. And my guess is probably when I retire in 15 years, we still won't be at doing 40,000 atoms of quantum mechanics. So we got to be to describe these systems. And so Adrian and I, let's see, so Adrian and I, about 20 years ago when he was a postdoc at Caltech, we developed this react force field. No one thought it would work. We asked for funding. No one would fund it because they said it's impossible. But fundamentally, well-trained systems, we get the barriers from the react force field good to about 0.2 eV compared to quantum mechanics. Now, the best quantum mechanics get barriers for lots of systems down to 0.05 eV. So it's not quite as good as the quantum mechanics. Let's see. So we're going to talk about that here. So it looks like a force field. There's a bond stuff, there's electrostatic stuff, and there's van der Waals stuff. The difference is the electrostatics, we use finite charges, not point charges. That means that atoms that are next to each other, they all have shielding. When you break the bond, then the shielding goes away and it's Coulombic. But when they're together, you have the shielding. And then the bond energy stuff, it can break bonds. We describe the bond energy in terms of bond order, in terms of bond distance. And so as you, oops, I guess I didn't put it in here. I didn't put it in here. I didn't put a curve in here. But the Raynaud's term, we can break the bonds and form new bonds. And so that's the fundamental thing. It's not trivial to fit the parameters because there are a lot of parameters in react force field, but it can be done. And we've done it for different systems. The code's in LAMPS. It's in lots of codes. It's been cited 4,500 times. Lots of people have used it. Generally works pretty well. No one funded it, so a little tiny bit of funding from DARPA. NSF, DOA, they have no interest in funding risky stuff like this. This looks at a new variation. So in the original react force field, we used a method of predicting charges we call charge equilibration we developed about 30 years ago. And charge equilibration has parameters that describe the ionization potential, electron affinity, the electronegativity, and things like that. They come from atomic calculations, and there's so it does pretty well. And then the new generation we call polarized charge equilibration. So the new generation, there's a positive charge the size of the atom, a Gaussian shape. There's a negative charge for the shell, size of the atom, a Gaussian shape. But the electric field can polarize the electrons away from the nucleus. And that actually works. You can't see it here, maybe, but in general, that works better than the QEQ. And it's really close to quantum mechanics. Let's just bring in point charges to different molecules and seeing how it polarizes in quantum mechanics and seeing how it polarizes in PQQ. PQQ was not really fitted to doing these quantum mechanics. PQQ, the parameters came from looking at atomic ionization potentials, electron affinities, etc. Here's the plot I was looking for. Yeah, so as the bond distance goes larger, the bond order goes down to 0, and forces go to 0. So we describe that overall relationship. And here's an example. So this is looking at the dehydrogenation of propane to propene. The catalyst is used for doing that. It's based on vanadium oxide. There are about 7 or 8 steps involved. And this is looking at the adiabatic potential surface. As you start with propane, you do the first step, you get a transition state, you get an intermediate, go to another state, go to transition state, intermediate, go to another state, transition state, intermediate. At the end, you've made 2 propenes from 2 propanes, and you've made 2 waters, and the vanadium is recycled. And so the point is, the reacts and the quantum mechanics are within about 0.2 EV. And that might seem maybe too big an error, but the point is, with the reacts, we can do dynamics at 350 centigrade, which is the temperature these things are done at. We can't do the quantum mechanics really more than 10 or 15 20 picoseconds. So we do the quantum mechanics. And what happens when you actually do the quantum mechanics at the operation temperature, some of the things you thought might be reactive, they don't actually react. They're too stable. The reactions occur at other sites in the system. So it's really important to do it at operational temperature. And this just shows in developing a reacts force field for the TFSI decomposition, we started off with sulfurs that were bonded to 2 oxygens and to a carbon and to a nitrogen. So sulfur 6. And by the time you fully react it, it's a sulfur 2. And so we have to describe all those different distances. And we use the quantum mechanics to train it, and ultimately they reproduce each other. So it's a bit tedious. This was done over a period of a couple of months, part-time by someone, by him, Moon Young Yang. So now we have a reactive force field. Now we can look at realistic systems. And so we're doing systems that range between about 40,000 atoms and about 100,000 atoms. This is a starting point to look at the SEI formation. So a total of 30 nanometers long, 4.5 nanometers wide in both the other 2 directions. And this is what happens during the reactions. So this is the charge on the lithium. So charge on the lithium in the electrode is 0. That's blue. And by the time and this SEI is about 10 nanometers. Right next to the blue, it's green. That's a charge only around 0.2 or 0.3. And then you get to 0.4, 0.5. And then finally you get to 0.8. So the charge of lithium in the ionic liquid is 0.8. And this just shows how that charge changes. So it's a width of about 10 nanometers. And what you can see here is actually there are 2 regions. Next to the electrode, it's kind of ordered. You can see that the carbons and fluorines have gone in and replaced lithiums, but it's still fairly ordered, that 2.5 nanometers. And then next to the electrode, it's very disordered and porous. You can see it's kind of porous-like. And people had talked about that kind of concept, that in the SEI, it's kind of crystalline-like, ordered, dense near the lithium electrode, and kind of porous-like near the electrolyte, but no data. I mean, just basically really no real objective information. So this shows how it works. So over 1 nanosecond, we start off and we heat it up to 300 Kelvin. There's a little bit of reaction heating it from 50 Kelvin to 300. The green is full molecules. Blue is partially dissociated. Red is fully dissociated. And as you go through the nanosecond, this is the range of the electrolyte, the SEI, 5 to 15, so it's 10 nanometers wide. What you can see is that you have some penetration of the partially decomposed into the electrolyte, and then you have more partially decomposed and fully decomposed the last 5 nanometers. So that's the lithium. Then this is the SEI molecule. CF3, SO2, nitrogen, SO2, CF3. This shows another way of looking at the decomposition, where we're just showing all the atoms of the TFSI. And you can see what's happening here is you're getting a lot of broken bonds in this region. And then this, yes?
Yeah, I'm just trying to understand like how you are trying to relate it to the function of a lithium-ion battery.
So this is not lithium ion, it's lithium anode. There's lithium metal, not ion.
Okay, lithium metal battery.
Yeah, so right now, lithium-ion batteries are pretty close to their full design limit.
Okay.
Lithium-ion batteries aren't going to improve very much over the next 10 years, probably.
Okay.
So the real potential is to use lithium metal, not lithium ion. And the problem with lithium metal, it's very reactive. And so that's what we're seeing here. This TFSI decomposes. When we make this SEI, it's 10 nanometers wide. We get all this kind of decomposition occurring.
So this is happening within 1 nanosecond. So
this is 1 nanosecond. This on a system that's about 30 nanoseconds, 30 nanometers long.
Right. So if I want to understand, if I want to try to think of it as a battery, so
Well, this is just one end of it. So we have another electrode we haven't put in here yet.
okay.
We're just looking at the problem with lithium metal anodes is that reaction at the lithium metal. So we want to understand that. There's no data. Experimentally, there's basically, they know there's some kind of SEI. There's no characterization. There's no atomistic characterization. Maybe eventually people do some kind of glancing angle experiment and they'll start getting data. Right now, there's not any. But qualitatively, the way people talk about it is similar to what we find. So we think we're okay. Yeah, so the that's the TFSI. The cation, not much change. Very little reactions to the cation, which we expect, except the cation moves in also. So the anion is reacting and moving over this 5 to 15 nanometer range here. For charge neutrality, the cation also moves in the first 7.5 nanometers. It doesn't go into the region where you have fully decomposed carbon and nitrogen, but it goes in this first 7.5. So you see two regions, 10 nanometers altogether, about 2.5 nanometers you call it inorganic, dense, ordered, and then 7.5 nanometers organic, porous. The inorganic are dominated by carbon and fluorine, and then the organic part dominated by nitrogen, oxygen, and sulfur. And again, qualitatively, people have talked about concepts like that. There's just no quantitative data. So this is consistent with the concepts people have talked about. So I think it's so now what we're doing is now putting a second electrode in. So now we have lithium, ionic liquid, and a second lithium. We're not putting the true cathode in. And then we're applying potentials to charge this end and discharge this end. And so that's ongoing work. So this is a modest system, 63,000 atoms. Let's see if I have. Yeah. So this is after a nanosecond, and so we're doing a constant E field across the system. We're still learning about it. We don't have bottom information here. We get an approximate diffusion coefficient for the lithium, and it's in the same ballpark as the experiment, which is good. But these are not final numbers. And now, so I had the idea that TFSI breaks apart, and you have carbon, nitrogen, fluorine, oxygen, a really messy system. Can we take maybe the best of those systems? So lithium nitride conductivity is not too bad. So could we pre-react the lithium with nitrogen and then protect the surface from reacting with the TFSI so it wouldn't decompose? What he didn't know is an experimentalist thought about this 2 years ago, and he'd already done the experiments. And then we're actually collaborating now. He's actually doing the calculations. So, and what he found was that it doesn't work to let N2 react with the lithium. It makes an amorphous system. It's not protected. But if you separately make lithium 3N and then put it on top of the lithium electrode, it is protected. And so right now, looking at the reaction of this system, we've actually gotten fairly well along here, but no bottom line numbers here. So this is our first atomistic information we claim about what the SI looks like. It's qualitatively similar to some of the ideas people have had. And now we're trying to redesign the system by pre-exposing the lithium to something to react with it. One idea is to use nitrogen, another idea is to use sulfur. So you have a collaboration with other people who are doing sulfur. And now we're trying to look at the charging and discharging. So now the second issue is on the electrolyte. So we want good conductivity. And these are the lithium conductivities of different electrolytes. So there's a series of systems that have conductivities somewhere around 10 to minus 2 Siemens. So these are good ones. We chose to look at this one. It's PS4 units with per forma unit 6 lithiums and a chlorine or bromine and a sulfur. And so the idea here, so these are solid electrolytes. So not liquid, they're solid. So we just talked about an ion and liquid. Now we're talking about a solid. And so there's a crystal structure. So we start with the crystal structure, and then we expand it to make it bigger so we have a more realistic system. So again, there's reactions at the interface, but right now we're going to characterize the conductivity. So that's a really important problem. So doing conductivity, what we do it two ways. We either just do dynamics and follow the motion of lithiums, or we apply an electric field and get the mobility. So this is using just doing dynamics at different temperatures. And so the idea is that we want to get to the range where R squared is proportional to T. That's the Fickian range. It takes about 20 nanoseconds. So people have tried doing quantum mechanics calculations. They can't get much bigger than about 100 picoseconds. So this is a range where there's not really, you're really not in a range where you're getting a true diffusivity. And what we get is a diffusion coefficient about 3.7. You convert that to conductivity, it's about 5.9. And the best numbers from experiment right now are about 5.1. So we're in the same ballpark. We did this as a function of temperature, and that's this here. If we get a barrier, cut off. We get a barrier of about 0.24 volts for theory, and these are 4 different NMR experiments, all of them good quality. They go in a range that are similar to the barrier we find, and similar to the overall conductivities, within about 1 order of magnitude. The problem is in these systems is the electrolytes are grains, and there's issues about going between grains and stuff like that. So an important number is the transverse number. How many, when you're doing the conductivity, how much is the lithium going and how much are the anions going? And what we find is it's 0.999. That's getting much better than that. So only the lithiums move. The anions at room temperature hardly move in 20 nanoseconds. Higher temperature is a little bit of migration on it. The transverse number goes down. So very hard. Yes, go ahead.
What is this plus?
Say again? Yeah, that's the transverse number. So that's looking at the total conductivity. So how much is the cation going in the direction you want the cation to go, and how much is by the other ions of the system? In this case, going the other direction. So you want something close to 1. For the ionic liquid I talked about a minute ago, where we had TFSI and the cation, transfer numbers are more like 0.6 or so. So there, the cations and anions are both diffusing. So this is good. All right. So per formula unit, for every PS4, there's 6 lithiums, a sulfur, and a chlorine. In the solid crystal, the lithiums are half occupied. So half the sites have a lithium, half the sites are empty. And we speculated that the reason why it's such a good conductor is that there are empty sites that lithiums can hop to. And so it's more complicated than that, because what happens as the lithium is migrating, there are 3 lithium atoms that are hopping between different empty sites. So it's a little more complicated. But fundamentally, the idea is that there's an equal number of holes and atoms. And so we thought, what if we made a compound that had only 5 lithiums per formula unit instead of 6? So now it has 7 vacancies per formula unit. And we thought maybe it would be a lot better conductivity. It's been made, but not measured. The conductivity has not been made. And what we find is it goes up maybe an order of magnitude. So by basically, and this is makeable. This is just replacing sulfur with chlorine. It's been made before. The fusion's not been measured. We have a collaborator in Hong Kong that's making it right now, and she's going to have measurements maybe at the end of this month or next month. We'll see. All right. So I want to shift gears a little bit and talk what we call grand canonical potential kinetics, or quantum mechanics, constant potential quantum mechanics. So yes.
So the conductivity is measured using something like the Stokes-Einstein relation?
There's 2 ways. One's done with NMR, and one's done electrochemically. And theoretically? We just calculate the diffusion. We just calculate. Yeah, we calculate this. So we go long enough until the R squared is proportional to T.
Right.
And then this line here gives you the diffusivity.
I see.
And we do it for all the ions. They're not plotted here, but we find in this system is about 2/3 of the ions go this way, and about 1/3 go this way. So many of the lithiums are not moving, not contributing.
Right. So, but the conductivity, is it, yeah.
Well, conductivity involves, of course, everything, not just the lithium.
Right, right. But I'm saying, like, once you have the diffusivity, you get it from the Stokes-Einstein relationship?
Yeah, we put in the charge with it and get a current.
Okay, got it.
So, yeah. So now I'm going to shift gears again. So normal quantum mechanics is constant number of electrons. But electrochemistry, the potential is what's adjusted. So given an experiment, you have applied potential, maybe 1.6 volts, and all the reactions. So for oxygen evolution, there are 9 steps of reaction, but they're all really operating at 1.6 volts. But every step of the reactant, the transition, the product, they're all at 1.6 volts. That means the charge is different. The charge of the reactant changes as you go through the reaction to the transition state, and changes as you go to the product. So to carry real electrocatalysis, we have to do calculations at constant potential, not constant electrons. There are 2 ways of doing it. One of them is that as you minimize in the system, you keep adjusting the chemical potential to keep it constant. But it's very laborious and very, very hard to do. And so a graduate student figured out an alternative way of doing it, which is pretty fast. So this is Yufeng Huang. So what he showed was, if you do a Legendre transformation, so if you add a number of electrons times chemical potential and transform from constant electron to constant potential, then you get a potential. It's a function of the, you get a free energy. It's a function of the potential. And at every potential, we optimize the number of electrons. So as you go from the reactant, the number of electrons in the reaction site may be 0.4. You go to transition state, it may be 1.5. You go to the product, it may be 0.5. So that's all considered automatically in this. And a bonus is that the fitting parameters that come from the theory, one of them has to do with the differential capacitance, and one of them has to do with the potential of zero charge. One has to do with energy at zero charge. So these have physical meanings. So this just shows how it looks. So in these calculations, we look at the free energy as a function of potential, and we transform to constant potential. And at every potential, we find the optimum number of electrons for that potential, for the reactant, for the transition state, for the product. And here's how it looks. The step in this case of forming the new OO bond at zero potential is a high barrier, a fairly late reaction. But as you make the potential more positive, the transition state moves towards the reactant, and the barrier goes down. And and I should say, this contrasts with how you look at. So you also talk about electron-coupled proton transfer. This is so the rates we calculate tend to be of the order of 1,000 per site or less per second. So we're looking at time scales of milliseconds. And this kind of view here, you're looking at electron transfer events, you're looking at time scales of maybe a picosecond. So you can do experiments looking at picosecond migration, and that may be useful for comparing to experiments, like where you photoionize a system or something. But we really want the net current as a function of potential. Yeah, so this, and this just shows that here's the transitions, the initial state and the final state. Here's the transition state of potential 1.6, and there's a transition state of potential of 0. So you've moved where the OO bond formation step occurs. And so now the key thing is our collaborator at Virginia, he makes single crystal nanoparticles. This is roughly 100 nanometers by 20 nanometers. It's single crystals. You get diffraction patterns show us a single crystal. He's done XF to show that the cobalt, it's about 10% cobalt. There are no cobalt neighbors according to the XF. So it's a single site, cobalt. And so the nice thing about that is we know what the surface looks like. So we've done lots of oxygen evolution reactions. nickel oxyhydroxide, the iron doped, various other systems, molybdenum disulfide, tungsten diselenide, and you know, some cases we can't even be sure what the surface we start with, and we certainly don't know what it's like at the onset potential. But in this case, the diffraction pattern says this is what the surface looks like, and so we think we know what the surface looks like, and so here we did is we put basically a monolayer or two of water, and then we use solvation models to treat the rest of it. We do the calculations of constant charge. We use VAS, so we use the VAS-Sol solvation model. We actually go and get the currents. We use JDFT, and we use the Candle solvation model, which is more accurate. But we have to consider, it's only one monolayer of water or so we have to consider the rearrangements of the waters. And this just shows, in this particular case, the various steps involve removing protons, getting new metal oxo bonds, things like that, forming OO bonds, eventually desorbing O2, etc. There's two competing models. Some people think that the oxygens in the O2 come from water, the sorbate model. Some people think it comes from lattice oxygen. And most of the early papers assume lattice oxygen. Every system we've done with these ground canonical methods, every system we've done so far is this one. And we have a collaboration with Jingzhuan Chen at Columbia, and he's going to do experiments where he does water 18. He's going to look at the initial reactions. Does he get O2 18 or does he get O16 18? So he's going to test whether we're right or not. We've already published, so our neck's stuck out. So we'll see what happens. So this just gives you some of the ideas of things that happen. The various steps as you're going along, you're deprotonating, rearranging, coupling, rearranging. So we go through all of, so to keep it fast, we do 1 or 2 monolayers of water, and we want to make sure that we've got the equilibrium structure. So now the oxidation state of cobalt depends on the potential. So if you start at 0 potential, it's a mixture of cobalt 2 plus and 3 plus. And then as you increase the potential, once you get above about 0.78, it's cobalt 4. And then at the onset potential, it's cobalt 4. So that means cobalt had 9 electrons. Now you have a D5. So, well, I guess I'm going to show the potential. So this just shows the overall. It's showing the overall kinetics again for some reason. I don't know why I'm showing this. I guess. Yeah, I just want to emphasize. So we calculate an absolute turnover frequency per cobalt, and this is taking the experimental value and getting the turnover frequency per cobalt. And basically, we're about 25% higher than experiment. It could be that we're right, and 1/4 of the sites are not active, or it could be the experiment, they're all active, and we're low by 0.03 eV. When I started looking at these problems, I never thought we'd get that kind of accuracy of quantum mechanics, 0.03 eV. Really amazing. One of the diagnostic features is what's called the Toffel slope. So if you take the plot the current as a function of the log, then if it's dominated by a Toffel reaction, it's about 30. And if it's, and what we find is 74. Experiment finds 72. And if we use the lattice oxygen model, the rate's down by a factor of 100 to 150, slower. Also, the slope is very different. So this is a diagnostic. And here's what's happening. So initially, when it's cobalt 2 plus or 3 plus, then you have, so cobalt 2 plus, you have an electron in the T2G orbital, the pi star orbital. Cobalt 3 plus, you've occupied the T2G orbitals. Cobalt 4 plus, you have a hole in the T2G orbitals. So at cobalt 2 plus and 3 plus, you can think about the bonding that you have in the oxygen, maybe 5 electrons in p orbitals, doubly occupied ones in the pi system, and then you have a covalent bond you're forming with a DZ squared orbital. And then in the pi system, you have a singly occupied orbital. So for cobalt 4, for the pi system, you have a singly occupied orbital, and in cobalt 4, this can delocalize. I think I have a better picture here. So cobalt 4 plus, we have 1 ampere spin in the T2G orbital. You get a delocalization of this state, which has the electron in the cobalt, and this state which has electron on the oxygen. This is what you want to make a new OO bond. You want unpaired spin on the oxygen, and the water loses a proton to another water or to another site and makes a new OO bond. So you need to have this radical character. This is how it works. It's actually a pretty good performance from these systems. We've done other systems. One of the interesting systems is chalcozenides. So these are things like tungsten, molybdenum ditelluride, tungsten ditelluride. In these systems, the experiments are done to have anion vacancies. These are not the edges. These are the basal planes. And so what happens, it's interesting that it's one site. There's one missing anion, but there are 3 metals exposed. So you can get 1, 0, 1, 2, or 3 metals. So the kinetics is very interesting. You can get kinetics that are not monotonic. And so in the experiments on this system, were done, these experiments, I've forgotten, they were done by our collaborators in Hong Kong or someone else. But we calculated onset potential 10 milliamps, 0.53, experiments 0.51. So these are within the tolerance of the methods. But it's interesting that these experiments, they stop short. They stop right here. They didn't go to this region where we predicted it's going to be non-monotonic. So another experiment we're doing, so with metal systems, these oxide systems, as you said, for the cobalt dope, we have a crystal structure, but iridium dioxide is one of the good OER catalysts, and generally it's polycrystalline. But our collaborator at Yale, Yang Xiao Horn, I don't see her name here, but anyway, so she's done 5 single crystal surfaces. So she's done 110, 100, all those surfaces. And then here we've done the kinetics for all 5 of them. So we calculate the free energy as a function of oxidation. We've got 17 different kinds of states we look at. They're going from fully oxidized to fully reduced. So we're really trying to nail the details of the chemistry, of what we predict and what the experiments measure. And so this shows what it looks like. So as you're changing the potential in this system, you're going from a case where the OHs go down and O dots go up, and later waters go down and OHs go up, and later waters and O's change to OH and O's, and later O's and H's go to O dots. And so this is the occupation of these sites. And you see distinct bumps in the occupations. Now what's measured is the current. So you take the derivative of this, and then these bumps still show up in the calculated current. So these are absolute comparisons. This is experiment and theory at the absolute rates. So within maybe 10%. And the experiment tends to wash out the peaks we see in the theory. We think it really is, again, a very good illustration that this is working pretty accurately. So, and of course, the key thing here is getting O dot. So these metal oxides, initially it's a bond to the metal oxygen, where there's all spins on the metal. As you go to higher oxidation, you start removing electrons. Eventually you get O dots. Along the way you get OH bonded to iridium. So we look at all that. And so, yeah, so I think, yeah, so this is a final comparison of the current. So these are absolute currents. No adjustment in the theory compared to the experiment. So the most reactive surfaces, the 100, the 001, 110, we're really right on the experiment. Really very pleasing. The surface that's the least reactive, they find more current than we find. We think its reason is this is so unreactive that the facet itself is not what's contributing. We think it's the edges, the step edges. That's not proved yet, but we think. So the high current for things we do very well on, the very low current, there's a discrepancy. I think it's due to the edges. Yeah, so we have another collaboration looking at what happens at metal surfaces with Shangfeng Dewan at UCLA. So what Don's done is he's made nanowires of platinum, about 1.5 nanometers wide, and then he's shown that as a function of potential, he effectively gets a pK of about 4.3. That is, he gets very high, the conductivity changes dramatically from very high conductivity, less than 4.3, to smaller conductivity. And his interpretation is that's what the pK of the surface water is. That lower pH than 4.3, you have protonated waters, and as you go above 4.3, you don't have them. So we wanted to compare to that. Now the issue is that these nanowires, they require about 30,000 atoms. So I'm sorry, about 3,000 atoms to actually have the solvent around the nanowire. So that's way too big for quantum mechanics. So what we did is we tested our REACT force field, which was developed about 20 years ago for platinum water. And we tested against quantum mechanics for the low index surfaces, 100 and 111. What we find is for the low index surfaces, we're off about half a pK unit. So quantum mechanics and the REACT force field, 0.5. So that means we're off about 0.03 EV from REACTs compared to quantum mechanics. But REACTs, we can do the whole 3,000 atoms. So this is looking at that system. So this is a validation that REACTs does pretty well. And then we use that to look at what happens in the 3,000 atom system. And what we find, 3,000 water system, 10,000 atoms, so we find a pK here. So it goes from about 3.8 right near the surface, and by the time you've gotten to 1.5 nanometers from the surface, it's gone down to 1. So it's a very big drop-off. Many experiments are trying to measure what happens near the surface. A lot of experiments have gotten down to about 1 micron. They don't see much happening. A collaborator at UC Irvine thinks he can get this by doing photoionization and measuring what happens for the ionized state. But right now, there's no data for experiment. I guess this is showing the same thing again. I'm not sure why I put them both in. So it's the same point. So here's what it looks like. These nanowires, it's periodic. It's 2 nanometers long this way, and about 1.5 nanometers in diameter. And this shows the hydrogen coverage as a function of potential. So we're going from a point, I think it's 0.9, I can't read it too well here, to about minus 0.04. What you see is at the more positive potentials, you have hydrogens at the facets, but not on the edges. And as you go to more negative potentials, now you start occupying the edges. So the edges are getting more stable as you go to negative potentials. And this just shows the predictions of the current, so getting the population, smoothing the population, and looking at the current from the calculations. And this is the experiment. So we get 2 peaks, one peak at 0.08 EV and one peak at 0.2. And we know now the 0.08 is the edges. And the 0.2, that's the facets. Now here's what they see experimentally. You don't know which one, what's going on at 0.04. Normally you can't measure the 0.04 because you get hydrogen bubbles. But in these experiments, that doesn't cause a problem. So this says that the system we're doing theoretically is probably just a little too big compared to what's dominating the experiment. And so here we've done the rates. The rates, so you saw the hydrogen coverage didn't get on the edges until to more negative potentials. The rates for the 111, 100 edge, that rate is much faster to make H2 than the normal facets. And the next most fastest is 111. So if you compare at a constant potential, say minus 0.05, the rate for this edge is 5 per second. This edge is 0.8 per second. The facet, well, I didn't put the numbers here, but the 100 facet is 0.05 per second, and the 111 is 0.0005. Maybe I have a slide. Yeah, this shows better. This shows the rates. So here's the rates. And so what that says is edges are playing an important role in the hydrogen evolution for platinum. So we've done studies, many people have done studies. When you do 111, we assume it's just pure 111. But this says the rate for pure 111 is down by a factor of 10,000 compared to the 111-100 edge. So we think that probably all the experiments here are dominated by edges. And so maybe it means you want to, if you're going to do a 111 facet, you should actually do a different index so you should optimize the facet, the edges. So another project we call the water drop project. So our collaborator Frances Houle, she's shown that for water, the pH is 7 when you have about 100 million waters in the drop. Pretty big drop. When you get below that size, then you no longer always have ions. So if you only have 1 million atoms in the drop, or even more so if you only have 18,000, then occasionally there's ions, but most of the time there's not ions. And so she claims that the pH is not really well defined. So we're doing two kinds of calculations. One calculation is we have a protonated water and an OH, and now we're doing dynamics to see how long it takes for them to recombine. We're doing another calculation where we see what the ionization potential is to have a proton and a water, so we can see how the pK, the properties of the system, changes the size of the water drop. And the motivation is we're trying to make systems where we have some kind of electrolyte, some kind of a membrane. And the question is, in these membranes, what happens if you only have little regions, like maybe 1,000 waters or 500 waters? How does that affect the overall properties of the system? And no one knows. So we want to try to figure that out. And we're also doing the same thing for CO2. So we have bicarbonate or various other forms of water. What controls the recombination? Once you have a bicarbonate, then you could add a hydrogen to this to get carbonic acid, or you could add a hydrogen to get CO2 in water. And so we want to get those. There's no data from the experiments. So for this, we're using the Rexfon force field. I'm not going to talk about the details of it, but Rexfon force field is a new generation reactive force field where we have a very accurate description of non-bond interactions, a very accurate description of the electrostatics, the PQAQ, and a very accurate description of hydrogen bonding. And with no empirical data whatsoever, we get a melting point within about 0.5 Kelvin, the heat of vaporization within 1%, the density within 0.001, entropy within about a few percent. So you get very accurate properties with no empirical data. And the most interesting thing about it is that you could ask, what data do we have on the structure of water? It's amorphous. What do you know about the structure of the water? There's only one piece of data that gives us structural information, and that's the low-angle scattering. So if you do neutron scattering, you can look at the actual oxygen-oxygen distribution, and this is what comes from the experiment right here, this black line. All the various force fields you have, they go way too high and fall down way too fast. They don't match the experiment. The only force field that matches the experiment is Rexfon. It was not built in, but we get basically the same distribution. So we think it's a very accurate description to use. And so what we're doing is we're doing water drops. So there's 18,000 waters, and then we treat it with the Rexfon, and then we have a protonated water somewhere, and then we have either protonated water with a shell of 4 waters around it, or we have an OH minus with a shell of 6 waters around it. And we have the waters have 4.7 waters around it. And then we're doing dynamics to look at the recombination. There's an experiment done back in the 50s where there's a very crude estimate of recombination. Brad Moore did an experiment around 2000. Basically, that's all the data there is. There's no real data on recombination. If you have an ion pair, how long does it take to recombine? And so, So this is looking at this water drop. The water drop's 94 angstroms in diameter, 18,000 waters. And so we start off with them 50 angstroms apart. Basically, they're just diffusing. 40 angstroms apart, just diffusing. 30 angstroms apart, just diffusing. 20 angstroms apart, just diffusing. We start 10 angstroms apart, they recombine quickly. And what happens is, yeah, so this is looking more at the shorter guesses, cases. So once they get it to about 10 angstroms, they recombine in 0.5 picoseconds. What happens is the OH minus and the protonated water, there's a GODDARD process where you transfer a proton from one shell to another one, a second GODDARD process, a third GODDARD process. That all occurs in 0.5 picoseconds. It recombines. A little bit further, 12 angstroms, you have diffusion for a long time, and then when it gets into 10 angstroms, boom, it collapses. So we think we can make a model from this where we have a capture radius of about 10, look at the diffusion rate of the protonated water and the OH, and actually predict how it's going to change with the size of the water drop. Yeah, so I think, yeah, this is just a movie of this. So we've done it with two cases. This is one shell of waters. So every time the proton moves to a new site, we take the new waters around that site. There are 4 around any one protonated water. There are 6 around any OH. And we've also done calculations where we have 2 shells of water. So 2 shells of waters, 14 waters around a protonated water, and 16 waters around an OH. And so we're trying to get all the data on this and just show what happens. 18,000 waters. That so we're trying to get at these small sizes real characterization, ionization potential constant, and of the dynamics. So I don't know. So yes, go ahead.
So, what is the background fluid in the all atoms table?
These are the Rex-Pond waters. So 18,000 Rex-Pond waters. So this is this system here.
So then, what are the big waters then? So those
Okay, I'm showing the quantum mechanics waters. So we have Rex-Pond for the waters that are not reacting, and then yeah. So that's this system. It's 9.3 nanometers wide, and then. And so then we're putting a protonated water someplace. We start off different distances between them. And then we're looking at and then as a proton moves from one water to another one, we take the 4 waters around that one. So we let the quantum mechanics waters change as the proton's migrating. So there's some GODDARD processes where it hops. There's vehicular processes where it hops. And this shows the recombination. So it says 2 sequential GODDARD processes, really 3, I think. All right. So now there's a question how we compare theory and experiment. Because experiments that are being done, they're going to be some kind of Raman experiment. You know, you put some, roughen up the surface so you can do a Raman studies. And so we want to compare the vibrational frequencies at the same conditions as the experiment. So very often for systems this size, the way you do quantum mechanics is you minimize the system and calculate the normal modes. But for water, that's wrong because the hydrogen bonding is very important. You've got to do the dynamics at room temperature and get the vibrational frequencies at room temperature. So how do we do that? So we use a process we call 2PT. We do the dynamics in a system. We do the velocity autocorrelation function. We take the Fourier transform and velocity autocorrelation function. That gives us a vibrational density of states. And then there tends to be states at 0 frequency. That's diffusion. So we pull out the diffusion modes so you have pure vibrational spectrum. And so this is what it looks like for water. For bulk water, it's a green line here. Water near the surface, I think it's a black line here. Yeah, bulk water. Bulk water. It says green. Anyway, there's big differences that go on next to a surface. And then, so this is comparing, so for the CO2 reduction, they take CO2 and convert to CO and convert that to ethylene. There are 10 steps involved. And there are various steps of the system. So the first step is the CO2 dissociates. You make a water plus a CO. And then the 2 COs combine together. That's the rate determining step. That's right here. So that's the biggest barrier. So that's the biggest barrier. And that barrier gets smaller and smaller as you go to more negative potential. So it's best at around minus 0.8, minus 1.0. It's not an electrochemical, but it's very sensitive to the potential. When you form this state with two hydrogens on the oxygen, HOCCOH, that has a big barrier to go to the next step. So going from here to here. And then there's another state where you have an HCCOH, and a state where you have CCH. They have big barriers. So the three states, this is the state we have CCOH, and the state we have CCH have big barriers. So this is the spectrum we calculate. So the blue lines are from the minimized structure doing the quantum mechanics of normal modes. The black lines are actually doing it at dynamics at room temperature. And what you see is that the hydrogen bonding broadens these modes. And so experimentally, they see a mode at 1180 and a mode at 1584. So we consider that the 1180 is probably this mode here, HOCCOH. They didn't do the isotope experiments to have a refinement. The quantum mechanics gets based below and above. The reason is that for CCOH, you have two CO bonds. Okay, a plus and minus combination of quantum mechanics, and they split. But because of hydrogen bonding, they're decorrelated. So the CH bonds are the average CH bonds. So this is how we compare to the experiment. We do the vibrational frequencies at room temperature. It takes 20 picoseconds. So after we equilibrate a system, it takes 20 picoseconds to get the spectrum. And we want to have, as experimentalists do, O16, O18, C13, C14, H and D, and then we can make a really rigorous comparison. So I don't know. Yeah, so this is looking at the mechanism, the whole mechanism. I sort of whipped through it there. You form a CC bond. You form this state that has a big barrier. And then you form this state, HCCOH, and either goes on the way to make ethylene or it goes on the way to make ethanol. The barrier is 0.06 EV difference. That 0.06 EV would correspond to a rate of, I think it's 11 times faster to make ethylene than ethanol. The experiment says that the difference is not 0.06, it's 0.053, I think it is. So it's pretty close. If I can just make one more point. So what I talked about, the quantum mechanics are all the calculations are less than 200 atoms or 300 atoms. And we looked at CO2 reduction. I didn't talk about the details, but for CO2 reduction on the very best alloy, which is pure copper, you get ethanol, you get ethylene, you get methane, you get hydrogen, you get all these things. And what you want is one product. And so Kanan showed that if you take a nanoparticle, 10 to 15 nanometers, you can get Faraday efficiencies above 70%. That's actually good enough. It could be a commercial. And of course, it must have something to do with grain boundaries because you have a nanoparticle, and you can see the grains here. And so how do we simulate that? Well, we use reacts. We grow the nanoparticle just like experimentally. We're doing CVD. We're using carbon atoms, copper atoms, I mean. And we grow it until we have 200,000 atoms. And by the time we get 200,000 atoms, we have about 10 to 15 nanometers. And if we take the X-ray diffraction from the reacts, it looks like the experimental X-ray diffraction. TEM looks pretty much like the experimental one. So we think this is actually mimicking a real system. It's actually interesting to see how it grows. If you're watching carefully, you see you start nucleating different places, and then they sometimes snap together as they grow together. So you use that. We did quantum mechanics. We did 200 sites. 4 of the sites had strong CO bonding, these 4. And 2 of those sites had a low barrier for making ethanol. So we thought, well, maybe these sites are important. The problem is that there were 11,000 surface sites. We did quantum mechanics on 200, and out of those 200, we found 2 we thought were good for ethanol. So how do we know that we're doing the right states? And there's another 10,900 we didn't look at. So how are we going to do that? So what we did is we developed a neural network to look at these systems, a 2-layer neural network. And then we trained it with those 200 sites we did with quantum mechanics on. And then we trained it, and then we made 200 new predictions and trained it with 200 And by the time we got 800 quantum mechanics calculations, our accuracy is down to 0.05 eV. And we figured, well, okay, now we have the whole system. Now we can do all 11,000 sites. So this is what it looks like. These are all 11,000 sites. This is showing the ordering of it. We also get the rates for these systems. And what we found is what's important is not just the grain boundary, it's twin boundaries. The twin boundaries can line up the HOCCO just right for stabilizing the intermediate. And so maybe that means you could take these nanoparticles, make them better by shearing the nanoparticle, because you should build in twin boundaries. No one's done that yet. So I know I've probably gone too long, so I'll just whip through the other slides. We're doing right now some really accurate calculations, collaboration with Jonas Peters and Theo Agapi. So Jonas and Theo have shown if you want to get high Faraday efficiency, you can put an organic film on top of the copper, and some films can get as high as 70%, 75% Faraday efficiency. So what we're doing is the kinetics for the pure surface, and then we're going to see how their organic modifies the chemical potential of water, CO2, and stuff like that. So the first question is, what surface do we do? So when I started, I assumed that probably it's a 1-1-1 surface of copper. But experiments have shown that the top 2 layers or so under reduction conditions are basically 100 light. I put in just one of them here, but there are many experiments show that the top surface under reduction conditions looks like copper 100. The second thing is, how do we look at the populations? So generally, one would calculate a Parbo diagram. You get the free energy for different states, and this is what it looks like. It says by the time you get down to a potential of minus 0.8, you got 1 molar. We get down to 0.9, you get 1 1/4 molar, and you get more as you go down. We did the kinetics. We looked at the first step of protonating in the surface, and the second step of adding proton to get reactions. And what we found is, in steady state, you only have half a molar. Parvo diagram here. This is equilibrium, not rates. No rates. This is with rates. So here it says every site is filled with a hydrogen, but in fact, in this range of potential, only half the sites are filled. So you have sites available. So I'll go through the slides really, really fast. So what we've done is we've done the free energies. We've done very accurate free energies. We put it into a kinetic Monte Carlo. Put all the steps in for all the reactions. And here's what we find. The final bottom line is that this is the CO production as a function of potential, ethylene, methane. There's experimentally about a 4-to-1 ratio. And so we think we're really understanding these systems. And now I think this is the last slide. So here are some of the people that did the work. Yes.
Hi, Professor Goddard. Thank you for the great talk. One of the things I was curious about was the difference between the barriers that you calculate from your constant potential formulation. It's also possible to extract this charge transfer coefficient from constant charge calculations, right? Like what the Norskov group does. So what's the difference in magnitude?
Well, one's accurate and one's not.
Right, that's true. But what's the difference in the magnitude?
Well, I mean, the point is, electrochemistry is constant potential, it's not constant charge.
Right. That's true.
Yeah.
I was just
So that's
curious
the main difference.
The difference in the numbers, how much it varies.
I think they're not very close.
Okay, got it. Okay,
So I think doing a constant electron you may be getting some of the wrong ideas.
Right, that's true.
Also, Norskov doesn't typically calculate barriers. He assumes the barriers related to delta G.
Right.
Very important. If you want to get rates, you got to get barriers.
Right. So this work is already published, the one you talked about
So
today?
the stuff I've shown here on the cobalt OER, that's published. The first paper we mentioned this new grand canonical method. It was part of a paper you're doing an application of molybdenum sulfide. It really wasn't done right. We should have had a separate paper on it. Mm-hmm. The work on the tungsten ditelluride and tungsten diselenide, that's been published. The work on iridium oxide, we're writing it up. So probably it'll be submitted another month or so, hopefully. So yeah, several papers we've now published using the Grand Canonical.
Right. We look it up. So you're doing this
Yeah,
through
if you
WASP,
just send me an
right?
email to WAG at Caltech, I'll send you some papers.
Right. You're doing this through WASP, right?
Yeah. So the problem is they're periodic systems. So we're stuck with using VASP, which means we're stuck with using GGA, PBE, which means because it does bad for van der Waals, we use the Grima D3 van der Waals. And we've shown that for molecular solids like solid hydrogen, solid carbon, solid phosphorus, PBE-D3 gives an equation of state that matches experiment up to about 100 gigapascal. So we think PBE-D3 is okay for doing the van der Waals. We do a lot of homogeneous catalysts. And we'd never use PBE. We'd always use hybrid methods, MO62X, various things. So right now it's a trade-off that if you use codes that use Gaussian basis functions, you can actually use hybrid methods. But the only codes that are available, like Crystal, are really crummy codes. So they're just hard to work with. They don't converge. And so we have to use VASP. And the Quantum Express is the same thing.
Right.
So,
Okay. Thank you.
This is really an opportunity to come up with. So the Crystal code using Gaussian basis functions for PBE is 3 times faster than VASP. Using hybrid, it's the same speed as VASP. VASP for hybrid is maybe 100 to 1,000 times slower. So using Gaussian base functions is a real opportunity, and it's just that these codes have just not been properly developed over the years. So it's too bad. There's really an opportunity there.
Right. Thank you.
Thank you, Professor. So I have a question on the TOEFL kinetics. How did you include
So which topic?
the plot that you have shown for the TOEFL kinetics, right?
Oh, the kinetics, and then
Yeah.
near the end.
So how did you say that it
this
is
this stuff here. This part, or earlier?
earlier?
Okay.
It's in the CO cobalt plus 3 and plus 4.
Oh, the way back. Okay.
Yeah. My question is like, how did you account for the mass transfer? Like, it is not limited by mass transfer.
No. Yeah. So we
How-
ignored it.
You ignored it. Like,
Yeah. Yeah.
how
So
did you
we
put
put
it
it in a little bit, or some simulations, but by and large, so like for the CO2 reduction problem that involves Jonas Peters and Theo Agape and the organics they're putting on the surface, the microenvironments, we're doing 2 kinds of calculations. We're doing quantum mechanics at the 200 atom level, looking at the fundamental rates. And I showed you, ethylene has a peak here and methane. And then we're doing force field calculations to look at the free energy of waters, CO2s, COs underneath the organic, between the organic and the surface. We think we can maybe see how the organics affected the chemical potential of water and CO2 and CO in that interface, and we can then maybe change those free energies in our quantum mechanics calculation and see what it would do to the rates. Does that answer?
yeah,
Okay.
thank you.
Hello. Hi, sir. So I have 2 questions. First, from this topic itself. So you were saying that lattice oxygen, when you go for OER, you found a better match with experiment when you got it from adsorption, right? Water
Yeah,
adsorption.
we did 2 mechanisms.
Yeah, but better performance with adsorbed
We just did
molecule.
both. So we did both mechanisms completely. If you check at the rate, 50 here.
Yeah, so clearly lattice oxygen model, this is differing a lot from experiment. So would
No, the experiment, good agreement. Not lattice oxygen.
yeah, that's what I'm saying. It's not lattice oxygen. So I'm saying, would it be like true for this system only or most of the systems?
So we've done 5 or so systems with OER. Every system we've done, it's absorbate oxygen. So as I said, Jinzhuang Chen at Columbia is going to test this. He's going to do it with O18 water He's going to see, does it get two O18s in the O2, or does it get one O18 and one O16? So he's going to do a test.
Okay, thank you. The second question was that in the CO2 reduction reaction, people generally go for CO-CO coupling.
Well, yeah, that's
So there are, I mean, but the CO-CO coupling is highly endergonic.
yeah.
So would
Here,
there be
I have
another
the, I have the
alternative?
interjection. Yeah. So first off, the barriers. This barrier, the CO coupling is 0.69. I've forgotten what potential this is at. This is probably at around minus 0.6. That's a big barrier. 0.24 to add the first hydrogen, 0.08 to add the second hydrogen. Now back to 0.63 again. So you can see this in the Raman. And then it's 0.44, and then back to 0.61 and 0.67. So we think we see this in the Raman. And so we think those may be done. But actually, so this shows, yeah, so this is CO absorption. It gets better and better as you go to negative potential. And then this is CO dimerization. So this is a barrier for CO dimerization. What you see is you go from 0 to -1, the barrier goes down dramatically. It's not an electrochemical step, but it's very sensitive electrochemical potential. And here's why. As you go to more negative potential, you start populating the carbon-carbon bond. There's the electron, you get electrons into the carbon-carbon bond. So it makes it easier to form the carbon-carbon bond. So this is the barrier of doing a CO dimerization. It gets better and better as you go to more negative potential.
Okay, so yeah, I'm not aware with the number of CO dimerization reaction activation energy. So I was aware when we have implicit solvation or gas phase dimerization of CO. Clearly, this 0.6 EV is not what I was looking for. I think it is in explicit. So that is why it is that.
So putting these kinetics together, when you get the full kinetic water Carlo, and putting that all together, what we find is that at basically the ethylene turns on around -0.8 and it dominates at -0.1, 1.0, also methane, and it goes back down again. And so one of the things as you go to more negative potential is the pH starts getting very positive at the electrode.
Thank you, sir. Thank
Okay.
you.
So in the water recombination reaction, so it looked like that as soon as the
Water recombination.
so the two quantum mechanical water and
Recombination. Okay.
yeah.
Sorry.
So in that particular case, is the reaction rate diffusion limited? And
Yeah, I think so. I
Does
think
it-
it's so we think that for that system, yeah. So we think for that system that when you're above say 12 or 15 angstroms, it's just diffusion. Diffusion of the protonated water in OH. There's no data on the protonated water diffusion or the. It's also hard to calculate because we have Grott's processes. So if we're trying to follow the water, the proton hops sometimes, and sometimes it's vehicular. So we're not quite sure how we're going to get the diffusion for the protonated water, but you can see it's basically diffusion. So now, so here's 16 angstroms. It's gotten close. It's already gotten down to about 8, so it's going to recombine. It's probably already recombined now. So you can think about it. There's sort of a cutoff about 10 angstroms. That's the capture radius. So when the proton and the protonated water get within 10 angstroms, boom, it takes less than maybe half a picosecond. And then so we could model it using the diffusion rate of protonated water and the diffusion rate of OH, and then any given distance between them, calculate how long it would be before they would be within 10 angstroms of each other. So it's not monotonic. So I guess I don't have it here, but we're right now doing a case. We're trying to pin this down. We started, I think, 11 or 13 angstroms, and it's gone a long time and it still hasn't recombined. So, it's statistical somehow.
So, since there are no further questions.
Well, maybe. Let's see.
Okay. The last piece of work, the CO2 reduction, what you were asking, is this a published work?
This, at the very end here, yeah. So this work is not yet published. Yeah, it's just about ready. I mean, Sunho is really a perfectionist. He wants to get everything just right, and so basically it's ready to publish. But so where we are actually is an interesting point. So we're just doing all this first principles. There's no data from experiment coming into it, and what we found until recently was that in the kinetics, we were getting the ethylene and the CO, but not the methane. It turns out the methane, the step of getting methane is you get an HOC. It's HOC, not HCO. You get an HOC that's stable around minus 0.8. And that HOC ends up making HCOH and ends up making methane. So if we leave out part of the mechanism, we should get the wrong answer. And so these are all okay now. And so I think we're probably about ready to publish it.
Okay. Yeah, so we can take over the questions during the high tea. So there will be high tea
Okay.
at the talk. So let's thanks Bill for an exciting talk. And we have some memento and thing from academy. So I'll.
Okay. All right. Okay. Ah, very nice. So I can catch up on ramen. So I talk about them all the time. But yeah. All right.